Swayam Prabha. Digital India. Educated India.
Dear viewers, up to now we have discussed various techniques by which ground data can be collected. In this session, I would like to introduce to you a technique by virtue of it the collected data can also be viewed in 3D. This technique is known as digital elevation model. Terrain information is essential to applications in many disciplines such as geography, land surveying, civil engineering, landscape architecture, Earth's environment, resource planning and management, and many other disciplines which require this information. The increasing availability of digital terrain data and advancements in computer technology in the last several years have resulted in a spectacular growth in the use of this particular component of geographic data processing. Digital terrain modeling may be approached in different ways. The mathematical approach aims to develop algorithms for terrain representation, contour interpolation and 3D visualization. The non-mathematical approach, on the other hand, tends to focus more on the applications of the digital terrain modeling techniques. Before we proceed ahead, it would be prudent to look at the definition of digital terrain model. The term digital terrain model, or in short DTM, was first introduced by Miller and Lafame in the year 1958, who defined it as a statistical representation of a continuous surface of the ground by a large number of selected points with known x, y and z coordinates defined by a arbitrary coordinate field. Along with the definitions, let us look at the associated terminologies with it. First is ground. This can be the solid surface of the earth, or the solid base or foundation, or the surface of the earth or the bottom of the sea. Height, measurement from base to top or elevation above the ground or recognized level, especially that of the sea, distance upwards, etc. Elevation, height above a given level, especially that of the sea, height above the horizon, etc. Terrain, tract of ground considered with regard to its natural features, extent of ground, region, territory, etc. Several terms have been coined to describe the methods and processes pertaining to digital terrain data. These include digital elevation model, digital terrain elevation data, digital terrain model and several others. So, let us look at them one by one. Digital elevation model, or in short DEM. The word elevation in DEM is the measurement of height above a datum. It implies to the absolute altitudes or elevations of the points contained in the data. The term digital elevation model and its acronym DEM are particularly widely used in North America to refer data sets containing regularly spaced elevations in the form of a lattice or a square grid. Digital terrain elevation data, or DTED. This term is used primarily as a product name for elevation data in the grid format that are generated by the former United States Defense Mapping Agency, now a part of the National Imagery and Mapping Agency NEMA. Now, let us look at what information can be represented through a DEM. A DEM could contain the following 4 groups of topographic and non-topographic information as follows. First, landforms such as elevation, slope, slope form and other more complicated geomorphological features that are used to depict the relief of the terrain. Second is terrain features such as hydrographic features like rivers, lakes, coastlines, transportation networks like road, railways, paths, settlements, boundaries, etc. Third is natural resources and environments such as soil, vegetation, geology, climate, etc. And fourth is socio-economic data such as the population distribution in an area, industry and agriculture and per capita income, etc. Let us look at the process of DEM. It is a process of mathematical modeling. In such a process, points are sampled from the terrain to be modeled with a certain observation accuracy, density and distribution. The terrain surface is then represented by the set of sample points. It attributes on locations on the digital surface other than the sample points need to be obtained by interpolation. Now, terrain description can be made by 2 basic types of descriptors. First is qualitative descriptors, which are expressed in general terms, so that they are referred to as general descriptors. Qualitative descriptors, which are those specified by numerical descriptors. So, let us look at what is general descriptor. It can be based on terrain surface cover such as vegetation, water, desert, dry snow, artificial or man-made features, for example, roads, buildings, airports, etc. and so on. It could be also based on the genesis of landforms. 2 such forms have been distinguished, each of which has its own special characteristics. First is endogenetic forms, forms by internal forces including neotectonic forms, volcanic forms and those forms resulting from the disposition of hot springs. The second is exogenetic forms formed by external forces including denudation forms, fluvial forms, karst forms, glacial forms, marine forms and so on. Based on physiography, generalized regions according to the structure and characteristics of its landform, each of which is kept as homogeneous as possible and has dominant characteristics, for example, high mountains, high plateau, mountains, low mountains, hill plateau, etc. Then it could be on the basis of any other classification deemed suitable. Then let us look at the numeric descriptors. These could be fractal dimensions, frequency spectrum, curvature, slope, relief and wavelength as a roughness vector. So, let us look at what is fractal dimension. Fractal dimension is a statistical parameter which can be used to characterize the complexity of a curve or a surface. Euclidean geometry, a curve has a dimension of 1 and a surface has a dimension of 2 regardless of its complexity. Similarly, a surface could have a dimension of 3. The fractal dimension is calculated as follows, where L is equal to C into R 1 minus D, where R is the scale of measurement, L is the length of measurement, C is a constant and D is interpreted as the fractal dimension of the curved lines. When measuring a fractal dimension of curved surface, R becomes the principal unit of surface used for a measurement and the resultant area is A and instead of L, and the expression becomes A is equal to C into R raised to the power 2 minus D. The next numeric descriptor is the frequency spectrum. A surface can be transformed from the space domain to the frequency domain by the means of a Fourier transformation. The terrain surface in its frequency domain is characterized by the frequency spectrum. The spectrum can be approximated by the following expression: S f is equal to E multiplied by f raised to the power a, where f denotes the frequency at which the spectrum magnitude is S f. E and a are the constants, that is characteristic parameters, which expresses the complexity of the terrain surface or profiles over all of the area. The next descriptor is curvature. The terrain surface can be synthesized by combining terrain form elements defined as relief unit of homogeneous plan and profile curvatures. Suppose a profile can be expressed as y as a function of x, then the curvature at position x can be computed as C is equal to the second differential of y with respect to x divided by 1 plus the first differential of dy by dx whole square raised to the power 1.5. Here the curvature C is inversely proportional to the radius of the curve R, that is, a large curvature is associated with a small radius. So, it means that larger the curvature, rougher is the surface. Hence, curvature can be used as a measure for the roughness of the terrain. The next numeric descriptor is slope, relief and wavelength. Roughness cannot be completely defined by any single parameter, but must be a roughness vector or a set of parameters. Relief is used to describe the vertical dimension of the amplitude of the topography, while the term grains and texture, that is the longest and the shortest significant wavelengths, are used to describe the horizontal variations. The parameters for these two dimensions are connected by slope. Thus, relief, wavelength and slope are the roughness parameters. Here in the figure below, we can see a function of the ground which has been represented by its slope at p and its wavelength w. So, here the slope of the ground can be expressed as 2 h divided by w, where alpha denotes the average slope angle, h is the local relief and w is the wavelength. Slope and wavelength together are recommended as roughness, terrain roughness vectors for DTM purposes. Land surface properties can be specified by convexity. These 5 attributes, that is altitude, gradient, aspect, profile convexity and plane convexities, are the main elements used to describe terrain surface. Amongst them, slope comprising of both gradient and aspect is the fundamental attribute. Gradient is measured at the steepest direction. The term slope or slope angle generally refers to the gradient at any specific direction. Slope is the first derivative of altitude on the terrain surface. It shows the rate of change in height of the terrain over a given distance. Having looked at these, now let us look at the whole DTM process. It can be seen that DTM is a multi-step process that is made up of the following sequences as shown in the figure below. That is, we have the real world, and from the real world the data would be acquired, by virtue of which a DTM would be generated. Now, this DTM would be subjected to certain form of processing. Thereafter, it would be subjected to some form of analysis, visualization and application. So, let us look at each of these processes which are involved in the process of DTM. Digital terrain data sampling. It is the structuring and the acquisition of the digital terrain data by photographic, cartographic and field surveying methods. Digital terrain data processing. It is the manipulation of the digital terrain to ensure their usability by GIS. Digital terrain data analysis. It involves the use of algorithms and procedures that restructure digital terrain data into useful geographic informations. Digital terrain visualization. It entails the development of algorithms and methods that will allow the effective display of the terrain to assist in spatial problem solving and decision making. DTM applications. It comprises of the practical use of DTM in different fields of science and technology. Let us look at the digital terrain data sampling. Acquisition of terrain data is a sampling procedure, and it is impossible to record each and every point on the earth's surface. So, there are two approaches to digital data sampling. First is systematic and the second is adaptive. Well, this particular slide shows the two schemes of data sampling. The real world can be subjected to systematic sampling, wherein the terrain data is stored as an array of elevation values, which we call it as digital elevation model. Here the data would be collected in a regular and well defined manner as shown. However, in adaptive sampling, the data of the real world would be collected in a random manner depending upon the need, and the data may be collected over irregular spacings in a random fashion, and the terrain data is stored as triangulated polygons, or what we call it as tins. In systematic terrain data sampling, elevations are measured at regular spaced intervals. The result is a matrix of elevation values that is usually referred to as a digital elevation model, or DEM. In adaptive sampling, elevation measurements are made at selective points that are representative of the terrain. These irregularly distributed elevation values that must be properly structured before they can be used for further processing. As the method of triangulation is used to build the spatial framework for storing the elevation values, this approach is referred to as triangulated irregular network, or in short TIN. The DEM and TIN approaches for data sampling are not mutually exclusive. They are established methods for the conversion of DEM to TIN and vice versa. The most digital terrain modeling systems accept both formats as input. In practice, the choice between DEM and TIN is governed more by the consideration rather than by the particular GIS or DTM application software to be used. These considerations include the nature of the terrain, the purpose of modeling, needs of specific applications and method of data acquisition. So, let us look at these considerations one by one. First is the nature of the terrain. The TIN approach is more suitable for representation of complex terrains where local changes are significant because systematic DEM sampling is unable to ensure that characteristic points in the terrain can be included. The next is the purpose of modeling. It is easier to perform spatial analysis, that is cartographic overlay with raster based DEM data than with vector based TIN data, but the latter method tends to produce more accurate results. The next is the needs of the specific applications. Some applications such as the production of the orthophotographs work more effectively with DEM data, whereas others such as the generation of shaded relief maps work better with the TIN data. The fourth consideration is the method of data acquisition. The DEM approach is more suited to terrain data acquisition by automated photogrammetric digitization, but the TIN approach allows terrain data to be collected more effectively by map digitization and field surveying methods. Having had a look at these, now let us look at the characteristics of a DEM. A DEM may be described by three elements: block, profile and elevation. The figure below shows a schematic representation of the elements of a DEM block. In this, we are having three elements. One is the block, the second is profile and the third is elevation. So, a block is used to describe the physical extent of a DEM. It is usually tied to a particular topographic map series, but does not necessarily always cover the same geographical extent. The next element in a DEM is profile. A profile is a linear array of sampled elevation points. The spacing between the profiles represent one dimension of the spatial resolution of the DEM. The other dimension is the spacing between the elevation points. There are three types of elevation points: regular points, first points along a profile and corner points. Of the three types of points, coordinate points stored only for the first points along a profile and the corner points. These coordinates are used to tie the DEM block to an accepted georeferencing system. They are also used to calculate the spacing of the profiles, that is in delta x and delta y, as well as the coordinates of the regular elevation points. Now, let us look at the characteristic of a TIN. In the TIN model, the terrain is recorded as a continuous surface made up of a mosaic of non-overlapping triangular facets formed by connecting selectively sampled elevation points using a consistent method of triangle construction. This can be seen in the figure below. where one can see the elements of the triangulated irregular network, wherein the basic elements could be an edge, a vertex and a mosaic of non-overlapping planar triangular facets. For the purpose of simpler mathematical interpolation, most tin models assume planar triangular facets determined by the three edges, sometimes referred to as a leg. Each edge is bound by two vertices, sometimes referred to as nodes. In a tin, these edges depict linear terrain features, that is, breaks, ridges and river channels, while the vertices describe nodal topographic features, that is, peaks, pits and passes. In addition to the difference in the method of sampling elevation points, the tin data model is distinct from the DEM model in two important ways. First, each and every sample point in a tin has an x and y coordinate and an elevation of z, whereas in a DEM the values, that is the location of the elevation points, are implicit in the data model. The tin data model may include explicit topographical relationships between points and their proximal triangles. Topological relationships play a significant role in the tin data model. By building these topological relationships, the totally unstructured elevation points as collected are converted into a properly organized geographic database suitable for terrain modeling applications. The process of triangulating thousands of discrete points is no trivial task, both conceptually and computationally. As illustrated below, a given set of elevation points may be triangulated in many ways. So, in figure A, we find there are 6 points which are there having elevations ranging between 90 to 120 meters. Now, what we can do is we can have different ways of triangulating the elevation points. Depending on the way of triangulating the elevation points, we can find that different forms of ground profiles can be generated, and this may, as a matter of fact, change the whole shape of the ground, as it may be a wrong representation because of the method by which the triangulation has been carried out. However, when this is representations of contour lines by interpolating it in the form of tins, we may find that the contours may also be of a different nature. For example, in the first case, the contours are running parallel to each other at an inclination, whereas in the second case, based on the method of triangulation, what we find now is that there is a peak. It appears there is a peak in between and the ground is in a circular manner around it. In the third case, it appears to be as if there it is a part of a valley. In the fourth case, it appears that there is a valley or a ridge line which may be existing, but in an altogether different direction in comparison to what has been depicted in C. If the resulting tins are used for contouring, very drastically different maps will be generated, as we have seen just now. The primary requirement in the tin data model, therefore, is to develop the necessary procedures that will ensure that the producing of a unique tin for a given set of elevation points. Delaunay's triangulation is the most commonly used methods for creating a network of triangles from sampled points over a particular geographic space for a tin, as it allows well shaped triangles to be generated. It is closely associated with proximal regions, also called as nearest neighborhood regions or Thiessen polygons or Voronoi polygons. Proximal regions are created as the result of subdividing a particular geographic domain or space encompassing a set of points into the set of convex polygons. Supposing we are given 3 points P 1, P 2, P 3 in a plane S as depicted in figure A. It is possible to partition the plane using perpendicular bisectors to the segments P 1, P 2, P 2, P 3 and P 1, P 3 into 3 proximal regions designated as V 1, V 2 and V 3. Each of these points contain one of the original point called as the anchor point, as shown in figure B. By definition, a proximal region is a polygon within which every point is closer to its own anchor point than the anchor points of all other regions. This means that any point located in V 1, for example, is closer to P 1 than to P 2 or P 3. The process of systematically subdividing a geographic domain in this way is called as Dirichlet tessellation in computational geometry. The resulting surface is known as Voronoi diagram or Thiessen polygon, as shown in figure C. If all the pairs of the anchor points sharing a common edge of the polygon in the Voronoi diagrams are connected, a network of triangle may be obtained, as we can see in figure D. The process of creating a network of triangles in this way is known as Delaunay's triangulation. The same is shown in the figure below, wherein the final Delaunay's triangle, through Delaunay's triangle, the final definitions of the polygons have been now made. The triangles obtained by this method having a unique property, that is the circumcircle that passes through the vertices of a particular triangle contains no other points in its interior, as it can be seen in figure E. This property, which is called as the empty circle criterion, is used as a mechanism to automatically construct a tin from a set of points in Delaunay triangulation. Delaunay's triangulation may be applied to 2D data as well as 3D data. In my next session, I will discuss how the input data for DEM is collected. Thank you.